to. Yes.
Can I go get my chemistry book and stuff?
Oh, sure. All right. So I mentioned this yesterday. You okay?
Yeah. Where'd it go?
The stores are dangerous. Okay, so we mentioned it yesterday, but I'll go through it again today. How you have different kind of spectrums. You have absorption spectrum, which would show the black bands of color that something is absorbing. Then you have the emission spectrum, which is what colors are given off. So in this situation, the emission spectrum, this sample is given off a green light, blue, purple, and red light. That's what you would see. And then it absorbs everything else. Continuous spectrum is all the colors of the rainbow with no gaps in it. Now I mentioned this before, Rutherford's model had a problem. So Rutherford developed a planetary model of the atom, which is what we see on here, where he knew that there was a nucleus with a positively charged particle and an electron orbiting around. Yes.
Couldn't this be explained by inertia though? Does the plane keep it out?
What do you mean?
Couldn't the fact that they don't go towards the nucleus be explained by inertia?
How would that
They
be?
keep getting pushed out.
They keep getting pushed out?
They want to go straight.
Well, they actually don't want to go straight though. They actually do want to, I mean, partly, right? But you have this stronger attraction for the nucleus. Definitely inertia does, like you're saying, like if you throw a ball, it wants to keep on going in that same direction. That's true. But you have a more powerful force that's pulling the electron to the nucleus, which it's hard to explain how that happens. Why? It's kind of like having, an open drain in the sink. You pour water in the sink and the water doesn't go down the drain. That's kind of the same situation here. It's how does that happen? It doesn't make any sense. Water goes down the drain because it's pulled down by gravity. Same thing here. The electron should be pulled into the nucleus. There's a stronger force pulling it in to the nucleus. Rutherford couldn't explain why it didn't do this. So physics said at the time that the electron should spiral into the nucleus. But Rutherford said, no, they don't do that. They are like planets. They stay at a certain orbit from the nucleus. And he knew that was true, but he couldn't explain why it was true. It wasn't until Niels Bohr in 1913 proposed a model that could explain this. So Niels Bohr knew that if you heated up different elements, you got different color bands. As you saw yesterday in class, we did the same thing. We heated up different elements, we saw different colors. You can analyze the colors of the flame and get different bands of color from that. And each element has its own fingerprint, its own unique band of colors that it emits. Niels Bohr knew about this. And so that's called the discontinuous spectra, where each sample gives you different bands of color, and not all the bands of color, just individual bands of color. And Niels Bohr proposed why that happens. He said that atoms only have certain allowable energy states that they're in. And you kind of like rungs in a ladder. You have a first step, second step, third step. You can only be on one of those steps. Those are different energy states on the ladder. He said atoms have the same exact thing. They have rungs that electrons can be in. And they can't be in between those ones. So we call it the lowest energy state, the ground state. So that would be the electron close to the nucleus. That's the lowest energy electron. And then as you get further from the nucleus, they're more higher energy. And then you can make electrons jump to a higher energy state. And that's called the excited state, when electrons are jumping up and down and going on to higher energy states. And so yesterday in class, that's what we saw. When we put the chemicals in the flame, Electrons got excited, they jumped up and down. And as they jumped up and down, we got the glowing flame that you saw. So electrons will create color and glow when they're excited.
So if you heat it up, electrons can bounce from band to band.
Exactly right. And as they're jumping up and down, you get the glowing that you see. And based on how high they jump, you get different colors.
So if you get a hotter flame, you can get them to be a different color.
Exactly. That's why we saw some people had yellow Bunsen burners, some people had blue Bunsen burners. That's to do with the heat of the flame. Blue flame is hotter than yellow flame. And then when you added a different kind of metal to the flame, you got different colors based on the electrons jumping up and down within the middle. That's also why iron gets red hot to white hot. You know, red hot iron, it can turn even hotter and turn into white hot iron. And that's higher energy as it goes from red to white. Now, it can emit other kinds of radiation, UV radiation, microwaves. We just can't see that, so we're not aware of it, but it can also emit other ones like infrared or UV. Like we all emit infrared radiation all the time. So if you have night vision goggles, it can detect infrared radiation, in which case you're looking at just the heat you're emitting. And you can look into, say, a building and see if people are in there based on the heat they're emitting. And that's how certain animals like bats can see in the dark, because they have infrared vision. And so to them, you'd be glowing in a cave because they can see the heat you're emitting off. Bohr said that an atom's energy state relates to the motion of the electrons, and that electrons move in only certain allowable orbits. So you can think of it again like, you know, being on steps on a staircase or rungs on a ladder, where if you put your feet, walk up a staircase, as you walk, you have to have your feet on a step. Or if you go up a ladder, you have to have your feet on the rung of a ladder to go up the ladder. Electrons behave in a similar way. They cannot be in between orbits. They can only be in one designated orbit. They can't be in two orbits or in between orbits. Now, you know, if you think about go up a ladder, you can hover one foot between a rung, right? But the other foot has to be on the ladder rung. One part of your body has to be resting on the rung of the ladder for you to stay on the ladder. The larger the orbit, the higher the energy of the electron. So electrons that are close to the nucleus are lowest energy. They have the smallest orbit. Electrons further from the nucleus have a higher orbit, higher energy. And so excited electrons jump to a higher orbit. And Niels Bohr numbered the orbits. A quantum number n designates energy level of each orbit. Number 1 is the lowest energy state, 7 is the highest energy state. So he designated 7 energy states in these orbits. Before we get for tomorrow, your periodic tables are needed for tomorrow. And really every class you should have them with you, but you need to have your own handout periodic table with you so you can write down something tomorrow. So be sure that you bring it, especially tomorrow to class, but in the future, have it always with you. You need to have your own individual periodic table you can write on. So have that with you, especially for tomorrow in class. So you can write down, actually tomorrow we do a lab, but just have it with you for Monday when we write down the notes. You'll need it for your test and for your final exam. So everybody have these down? Okay, so what he said is this, that each orbit relates to an energy level. So this is energy level 1, 2, and 3. And that this would be higher energy because it's further from the nucleus, it has a higher orbit. It has to go faster than these ones do. you don't really have to write this down or draw this, but you can if you want, but just the main idea is like we've already talked about, that each orbit designates an energy state. That's the main thing to take away from this picture. And that he saw 7 orbits in atoms. And even though it looks like it's 2-dimensional, it's really not. You can think of it more as a sphere of orbits where the electrons can travel through a certain 3-dimensional space and not just in a 2-dimensional orbit. It's kind of like having a balloon, you know, where the electron can be anywhere within that balloon. Think of it more like that. So Niels Bohr proposed this idea that when you see different color bands, what is happening is electrons are going between orbits and giving off those colors. So if you see a red band of color, he says that you have an electron jumping from number 3 to number 4 energy level. And as it comes back down, it emits energy in the form of red light. And that's what we see as red light. So when you see the light, the electrons are emitting that energy and coming back down into orbit. So they gain energy, you don't see that, but what you do see is when they come back down and they lose energy, that's what you see as a glowing color. So if an electron moves from number 2 to number 7 and comes back down, you're going to see blue light. If it goes from 2 to 6 and comes back down, you're going to see green light.
So whenever you say the electrons move, does it mean that they just like switch, like positions with?
That's right, they jump to a different orbit.
And so can you make an atom unstable by moving like the electrons?
It can become unstable for a little bit of time, but it becomes stable again very quickly. So yes, for that short amount of time, it would be unstable, but it becomes stable when it emits energy. And so it becomes stable very quickly as it loses energy and goes back down to its ground state.
Okay, and then for the orbits, are they like, are they actually like real things, or are they just like, so like, are they like actually part of the atom, or are they just, like,
Yeah, that's a good question. No, they're not. It's kind of like planets in the solar system. You can't see an orbit, right? The planet just travels around, but you don't see a line that makes the planet go in that line, right?
Okay.
It's like that, where it's not a visible thing. The electrons travel around in a circle, but we don't see a boundary. We don't see any kind of shell that keeps them there. You also have, so this is the visible light series over here. Infrared actually these are infrared lights, not actually red lights. So this would be invisible to our eyes. Ultraviolet radiation can also be emitted. And so atoms can give off not just visible radiation, but also other kinds.
For all we know, is this true?
We're pretty confident it's true, yeah. I mean, because all the calculations we've done confirm this is true.
So Bohr was right?
So it seems like he is. Of course, in the future, something could come along and we realize, no, he wasn't, but we're very confident at this point that this is true. Because everything that we've done makes sense. All the experiments we've done, calculations we've done, all confirm this is true. Now, he wasn't totally right, though. We're going to learn about some things he was wrong about, but he was right about this part. Now, it only really worked for hydrogen, though. Like this model for the planets, the electrons being like planets around the nucleus, only was perfect for hydrogen. So the other atoms, it broke apart. So we knew he was missing something. So he's on the right track with the idea of electrons jumping up and down between orbits and giving off light. He was right about that part. But what he was wrong about was the idea of just these 2-dimensional orbits. What also was missing besides just that was they couldn't explain why electrons change the chemical behavior of atoms. They knew that the kinds of electrons atoms had could change how they operated, how they reacted, but nobody knew why. So as I mentioned, the thing he was wrong about, the thing that he was missing, was he was wrong about circular orbits. He envisioned electrons going in a circle around the nucleus. That part is incorrect. They don't go around in circles. Well, they can, but they don't usually. They usually have more complex patterns they take than just circles. So the general idea is correct that electrons orbit the nucleus, but what he was wrong about was that they go in circles.
What do you know that they don't go in circles?
Based on the math that we have, the math falls apart. If we say they go in circles and we use equations, it doesn't work.
What do you mean, like the time it takes for it to go around, it doesn't have?
It has to do with the energy values, yeah, the time too, the velocity, all the calculations that we have, they don't work if we say that they go in a circle. They have to go in different shapes for it to
Or
work.
we don't actually know what shape it is?
Actually, we do know, yeah. So we were going to talk about the shapes, but they're complex shapes. You can see on page 154 some of the shapes they take. But this shows you some paths they will take, and they're not always circular. They can be circular. You can see some of them are circles, but they're not always. And that's why he's right about hydrogen, because hydrogen actually does have circular orbits. And that's why hydrogen worked for his calculations. But the other atoms are more complex and they don't just have circular orbits. So his idea was right, just the shape was wrong. The other thing he was right about was the idea of quantized energy, which means that electrons are in different energy states. That you have rung 1, rung 2, rung 3. The electrons stay in one energy value and they can jump between them, but they can't stay in a mid state between energy levels. So either in stage 1 or stage 2 or stage 3, they're not in halfway between those two stages. A little bit later on, about 10 years after Niels Bohr talked about this, Louis de Broglie, 1924, said orbitals seem to have a wave-like pattern. So this also added on and helped find a missing piece to Niels Bohr, his hypothesis about the atom, that electrons also have a wave property to them. So Louis de Broglie proposed this idea that electrons behave like waves. In this equation, you'll want to write down all of this, the symbols and what they mean. You'll want to understand this. We won't ever use this equation in math, but you do need to know what the symbols represent and what this equation is telling you. So what he said is this, that wavelength equals Planck's constant, which is h, divided by the mass of the particle times its velocity. What does that mean? It means that anything that has mass and velocity has a wave pattern to it, a wave nature to it. And so that's what he said. He said every particle has a wave nature to it, including humans, including large objects, houses. He said everything has a wave nature to it. It's just that things that are very large have a very, very low wavelength, and so it's almost indetectable, or is indetectable to us. We can measure it, but it's so low it's pretty much non-existent.
So like just random objects have wavelengths?
That's right. They're just so small that we can't, I mean, we can measure it, but we can't really experience it. We aren't aware of it. And so things vibrate back and forth. Basically, that, you know, objects, basically what that means to have a wave nature is that you have oscillating movement, vibrating movement. What it also means that you can't be confident where something is because it's constantly in motion. And so you have some uncertainty about where that object is at any one time. But it only is a problem for things that are very, very small, like electrons. For large objects like soccer balls and for people, we're very confident about where that person is, where the soccer ball is, because their wavelengths are so small, it's really almost zero. And so we can be very confident about where a person is because there's not much movement to that person.
So let's say it sped up and the table was like moving. Would we see it just go from one place to another instantaneously, or would it like?
Well, it definitely would have to take time for it to travel between two places. But what would happen if it got faster and faster is it become more like a wave, which would mean we would be less certain about where it is at any one time. It would be hard to pinpoint its location at any one time.
So it'd be like a blur.
That's right, become more blurry. It would give off glowing light. So when things go faster, they start to glow. And you'd see it, if it comes towards you, it would glow blue and go away from you, glow red. And so you'd see it start to give off light and glow, and it'd become more blurry. It'd be hard to distinguish where it began, where it ended. Its boundary wouldn't be as clear. You wouldn't have a clear boundary of the object. It would just kind of be more like scattered, and you'd have a hard time being certain where it was. And so this equation, the de Broglie equation, predicts that all moving objects, whether they're big or small, have wave properties to them. But you only see this really be an issue when this things like electrons.
Do you think that we'll ever be able to travel at speed?
Probably not for a person. Yeah, I don't think so. I mean, just getting a machine that can do that, I don't know if that's possible. So that would be the big issue to come. And after you get the machine, getting a person to go at that speed would take a long time to get there. Because, you know, accelerations be pretty slow to get to light speed for a person to survive it. So I doubt it. I'd be very surprised if we could. I don't think we have the equipment to get to light speed. It would take way too much fuel and energy that we just don't have at this point. Oh. So this equation, you used to be familiar with it. So on the test, you might see this equation. It might ask you who developed this equation, or what does it tell you? And you just have to know it's de Broglie's equation, and that he said that anything that has motion has a wavelength to it. That's what you would need to know for the test.
Wait, what did you say that we have to know for the test?
Oh, basically just the name of the equation. So they might just give you the equation, ask you the name of the equation or who developed it, and then what it tells you. And so it says that things that are moving they have wavelengths associated with them. Anything that has motion has a wavelength.
Wait, this is gonna be on the final, right?
Well, yes, I'm sorry, the final, because we won't have a chapter test for this, yes. Next week, we won't have a final, or we won't have a chapter test next week. I'll give you a review packet, but we won't do a chapter 5 test. We won't have time for that.
Wait, is the name of the equation just?
Yeah, the de Broglie equation, yeah. So this is valid for all moving particles, but anything that is large, you know, things that we can see with our own eyes, have too small of a wavelength to be detected, and it's really pretty much zero. Like for a car, tend to think of 38th power, and which is incredibly tiny. We have no way to measure that. An atom is 10 to the negative 10th power. And so this is about, billions and billions times smaller than an atom.
If we got something moving fast enough, could we detect the wavelength?
Yes, that's right. So the faster it goes, yes. So if it goes near the speed of light, you would definitely see detectable wavelength. You'd see it glowing. It would start to blur. So then we definitely would have a wavelength that you can measure
So
or that
if
you can
someone
detect.
went the speed of light, would like the blurring, would they like blur out of?
Yeah, that's right. They would be a blur. The boundary of where they start, where they
Would
ended.
they become invisible though?
You could see a glowing light. Now they become very, very thin. Like, it'd be hard to see the actual person, but you'd
So
see,
they look like a comet.
yeah, very similar to that. Yeah. Next one, Werner Heisenberg. Have you heard about him before?
He starts some hot dog company.
Hot dog company. Well, why hot dogs?
Isn't there a hot dog company called?
Oh, maybe. I mean, Werner, or Heisenberg, I mean, it's a German name, so they do lots with hot dogs, so maybe. So he said it's impossible to take any measurement of an object without disturbing it. So because of that, think about it's strange to think of it that way, but even observing something by looking at it, you're disturbing that object. So even the act of observing something disturbs that object. Why is that true? Well, when you look at something, what has to happen? You have to have light beams hit that object and then go to your eyes. And that's how observing something disturbs the object.
Wait, how does it disturb an object if stuff is only coming to you and not back?
Well, because it has to bounce off and get to your eyes, right?
Yeah.
And then when it does, so it bounces off an object and then goes to your eyes.
So looking at it does not disturb it, but knowing that you can look at it means that it is disturbed. Right?
Well, it's strange because it seems like there's some experiments that have happened where it seems like even just the person looking at it actually can change it too. And we don't know what that means exactly, but not just, shooting it with photons or electrons by putting a light beam on it. What they've seen is that you can have a light beam shine on something and not watch it, but then you can have something actually watch it and it will change its behavior based on being watched. And we don't know exactly what that means yet, but by having an observer, just the act of observing and taking in information, you actually change the nature of objects.
So isn't this kind of true in like the way like people react?
Yeah, that's different, right? Because people are conscious, right? And so we are aware of people watching us, right? And we'll change based on who's watching us, right? Is that what you're talking about? Or is it different? Like,
No,
is it talking about like when you know you're being watched, or you
if
mean something
someone-
different?
If you don't know if someone's in a room or something, but you can feel something is different.
Right. Yeah, we don't know what that means. Now, it could be that you're hearing some sounds that, you're not subconsciously aware of. You could be, I mentioned this earlier, I think to all of you, that people emit different chemicals. And those chemicals, are also aware of those chemicals. And so it's possible that that's happening too. Did I tell you this before about they were watching movies and they had different chemicals secreted based on if it was a funny movie or a sad movie. So it's possible you're aware of those chemicals that person's emitting. Or it could be something else or we don't know yet about human biology. Maybe electricity is being sent off from that person that you can pick up on.
A sixth sense.
Or it could be your guardian angel, or, it could be spiritual, supernatural, that's letting you know about that person. We don't really know for sure. But, it seems like there is some kind of connection between twins. It seems like that twins especially are very well connected to each other.
Wait, I think that was a myth.
It's not a myth. Like Miss Mahaffey, did she ever tell you the story about her and her twin?
One day they're all down here.
Oh, I know. But one of them was, I forgot who it was, but one of them was in a car accident and the other one was not there. But they knew immediately something was wrong with that twin. Like they just knew something horrible had happened to that person. And there's no way to explain that. And it happens all the time. I hear so many stories like that twins just know when they're sad or when they're in trouble. And there's no way they can know that because they weren't close at that time when that happened. So it seems like there is something, whether it's God letting you know about that, or an angel, or something else we don't know yet about. So there's something that we're not aware of that communicates with us about people. Heisenberg uncertainty principle. He said that it's impossible to know both the velocity and position of a particle at the same time. So in large objects, your uncertainty is so small, it's really nothing. So like you're watching a ball, like a soccer ball, go across the field. You can be very confident that you know its speed and position because it's just such a large object. It's easy to pinpoint its speed and location. But if you're dealing with very small objects like electrons, the uncertainty gets very large at that point, and it's very difficult to pinpoint its velocity and location. Yes.
So if we get to the speed of light, could the person figure out how fast they're going?
What do you mean?
If someone got to the speed of, or if we got someone going at the speed of light, could we figure out how fast he's going?
Oh, I mean, you get an idea, right? But what he's saying is you can't be confident, like you can't be exactly precise. Like you can get an idea, a ballpark of how fast they're going, but he's saying that the faster they go, the harder it is to pinpoint. And that's, again, it's easier for large things like a person. Maybe dealing with really small things, so it's a lot harder to do that. But he means you can't be precise to the nth degree. You can be somewhat precise. You can have an idea of their speed, but you can't be 100% accurate. For an electron, the uncertainty is 10 to the negative meters, which is about 10 times the diameter of the atom. And so the uncertainty for a small particle is an issue because the electron is confined to an atom, and we can't know anything about its location if we don't know within the boundary of the atom where it could be. It's kind of like, I can hear Miss Liskey's voice, and so I know she's somewhere over there in that room, but I don't know exactly where she is. I can't say, is she at the whiteboard? Is she at her desk? Is she at a student's desk? I can't know that. So it's kind of like that. It's like knowing that they're in a room, like the electron's in this room, in this atom, but we don't know within the room where it is exactly. We just know it's somewhere in there.
Then how do we know what shape they move in?
That's a good question. Based on math, we can determine that. So we can't see it. You can't see the shapes, but based on the equations, it's only a shape that makes sense.
So like, how like all these like weird theories and like conspiracies about like telekinesis?
Yes.
Is there like any possible way that we can, or like any kind of like explanation?
Yeah, I mean, there are, mostly it'd be supernatural explanations, I think, that angels, God has given you that ability. But outside of that, yes, there are ways, there are particles that can be transferred very large distances that can communicate with each other. We can see electrons, you can move one electron in one place in the world, and that electron will feel that electron's movement hundreds or even millions of miles away. And so that's evidence that people who are in, like twins, for example, that have a strong connection, possibly their particles can move, which can then affect the other particles in their twin, which could then maybe make a way they could, we don't know, but they might communicate that way. So that's one possibility. So yes, it is possible that it could be a physical thing you can experience and scientifically explain without having a supernatural reason for it, or it could be supernatural too. But I just, there's so many stories that it's happened that I believe that it does happen. Just we don't know how exactly it happens.
So they have some sort of like mathematical handshake?
Maybe, yeah. I mean, that's one theory. We know for right now that you can have particles that are it's called entanglement. Particles are entangled. And those particles are intertwined to the point where they can be separated hundreds, millions of miles away. And if you move one particle, the other one will move in response to that particle. And so you could have, say twins be entangled, where their particles, if they're moved in a certain way, could affect the other twins' particles, which could then go into a thought that they have. It could go into a feeling that they have. That's one way that could happen. Electricity, we think through electricity. Electricity is how we think. So electricity could be transmitted too, and that could also change our thoughts or feelings about things.
I think I've heard of this guy.
Oh, Schrodinger?
Yeah.
Did you hear about-
Did he do something with his cat? Like,
Yeah, so Schrodinger's, yeah, so he didn't actually do this, but it was a thought experiment that he did. So Schrodinger's box, that's what he talked about. That basically what he said is this: you have a cat in a box, and it's locked up in this box with a vial of poison, and the poison bottle is open, but the cat has not drank it yet, and you close the box up. We'll come back later to the box. Is the cat alive or dead? Well, you can't know until you open the box, right? That cat can be dead or alive until you open the box. But once you open the box, then you know if the cat's dead or alive, right? And so what he was saying, he said it's really absurd, but he was trying to just show how crazy quantum mechanics is. Because what quantum mechanics says is this, that you can have a particle that's both a wave and a particle. But once you observe it, it becomes one or the other. So before you observe it, it's both a particle and a wave. Once you observe it, it becomes one or the other. And so it's kind of like the cat, the same thing. The cat is dead or alive. Once you observe it, then it becomes dead or alive. That's kind of the thought behind that. But he was not using it to make a point, except to just say that quantum mechanics is just absurd. So Aaron Schrodinger, 1926, developed an equation that treated electrons as waves. And notice that this applied to all atoms. This is called the quantum mechanical model. So basically what it said is that we can't know for sure where electrons are at. We can have an idea of the space that they're in, but we can't say for sure their location or the path they're taking. Again, it's just like having a person in a different room, and I can hear their voice, so I know they're in that room, but I can't tell you which way they're walking in that room. I can't tell you where they are in the room. I just know that that's where they're at. And that's kind of what Schrodinger is saying too. We can have an idea of the boundary of an electron and where it might be at any one time, but we can't say anything more than that. We can't say for sure what it's doing within that boundary. So he deals with probabilities. And what I could say, go back to the example of Miss Alinsky in her math room, I could say, well, probably she's going to be at the whiteboard. That's most likely where she's going to be. And so I could guess that's where she'd be. I could be wrong about that though, but most likely that is where she would be at this time. And so that's what he says too. He can pinpoint most likely places for electrons to be at any one time, but they can be outside that boundary too. So he said, so orbits are two-dimensional planetary models. What he proposed is orbitals. Orbitals are three-dimensional regions where the electron might be, or where it's most likely to be. And so this right here shows you a snapshot of the electron's path over, it's a time-lapse image of one electron and where it was over a course of, say, a day. And you can see most of the time it's in the very center. That's where you can see a very dense blue. Some of the time it's in this area. Less of the time it's out here, and it's never outside of that boundary. And so that gives you an idea of where it might be. And so chemists draw a circle around where the electron is 90% of the time. That's called the orbital. It's where the electron is 90% of the time. It's a three-dimensional region, and so think of it as like a sphere, or like a balloon, or a room where the electron is. But it's not a physical boundary. It's not like a wall that keeps it out. It's just that's where it stays. Yes, no.
So is the orbital the place where it's just,
Yeah, basically, it would just be like this
Oh,
right
right,
here. I
okay.
mean, 90% of the time, because it's gonna be out here too some of the time, but it's 90% of the time it's gonna be really within this area. Okay, we'll stop here for today. Tomorrow we're doing an experiment. 5 minutes to go in class. So for homework today on page 155, just do a few of the questions. Don't do all of them. I want you to do 15, 16, and 20 for today. 15, 16, and 20 on page 155.